Hey guys, it's your daddy Big Dave back here again to try to help you out a bit with exam number one. Again, a wonderful day here in Morro Bay. A little foggy, which is really normal here. A little sun, a little fog. Love it. All right, so on your exam, you are going to type out the vocabulary words and their definitions. Your book is perfect for this. Okay, and then I'm going to go through the study guide with you right now to give you a lot of help, a lot of hints, and then we'll talk about the essay also here in just a moment. So let's start here. Know the most abundant gases in the atmosphere. That would be nitrogen at 78% and oxygen at 21%, N2 and O2. The environmental lapse rate, that's the rate of temperature change as you go up on an average day in the troposphere. The troposphere is the lower layer of the atmosphere where I'm sitting right now. On an average day, as you go up, say in a hot air balloon or something, you're going up and the air's not moving, it'll cool off at about 3.5 degrees Fahrenheit per every 1,000 feet that you go up. You kind of experience this when you go up to Three Rivers or beyond Three Rivers, even up to Sequoia National Park, where it definitely will get cooler as you go up. That's a little different, but kind of the general idea. So it's a rate of temperature change as you go up on an average day, because the numbers will change, but on an average day it's 3.5 degrees Fahrenheit per every 1,000 feet. The Earth makes an elliptical orbit around the Sun. The average distance from the Earth to the Sun is 93 million miles. There's a time, though, when we're closer to the Sun and a time when we're a bit further away. So when we're closest, that's referred to as perihelion. And surprisingly enough, that occurs in early January. Aphelion is when we're furthest from the Sun, and that generally occurs in early July. How does the majority of oxygen get into our atmosphere? That's through photosynthesis. Understand the terms solstice and equinox and when they occur. There are two solstices, and they would occur on June 22nd and December 22nd. The two equinoxes occur on September 22nd and March 22nd. Okay, so when you have the solstices, the June solstice, the sun is directly overhead at the Tropic of Cancer, about June 21st, 22nd. During the December solstice, the sun is directly overhead at the Tropic of Cancer in the southern hemisphere. On the equinoxes, both of them, the sun would be directly overhead at the equator on March 22nd and September 22nd. When does Visalia experience its longest day and its shortest day? The longest day of the year is the June solstice, June 21st or 22nd, during that time frame. The shortest day is during the December solstice, that's December 21 or 22. What would happen if the Earth's rotational velocity increased? Okay, well, day and night would be shorter, there'd be more days in a year, and I might be able to jump higher again. Because the faster the Earth rotates, it's like a merry-go-round going faster and faster wants to throw you off. The faster the Earth would go, the higher I could jump. And as I age here ever so gracefully, right, I'm not able to slam dunk a basketball anymore, which is very disturbing. But if I could increase that rotational velocity, I might be able to jump higher, right, defy gravity, and slam dunk again. Okay, how much is the Earth's axis tilted? It is tilted 23.5 degrees away from a line that is drawn perpendicular to the plane of the ecliptic. Okay, as the Earth revolves around the Sun, it revolves around on a nice geometric plane called the plane of the ecliptic. It doesn't go up and down like this, it goes around like this. If you drew a line straight up or perpendicular from that plane, right, and then the Earth's axis would be tilted 23.5 degrees away from that line that's drawn perpendicular to the plane of the ecliptic. So the plane of the ecliptic is a constant plane in which the Earth revolves around the Sun. Draw a line perpendicular to that, and then get the Earth's axis 23.5 degrees off of that. All right? Understand what happens during a temperature inversion. Generally, in the troposphere, where I'm at right now, the lower layer of the atmosphere, as you go up, it cools off at that environmental lapse rate. But sometimes it gets warmer as you go up. That happens a lot in the Central Valley, the LA Basin, Mexico City. If it gets warmer as you go up, that's referred to as a temperature inversion. What might happen if the rate of the Earth's revolution increased? Well, the year would be shorter, the seasons would be shorter. What happens at the Arctic Circle on June 22nd? Well, On June 22nd of the Arctic Circle, the sun will never set. That's how far north you'd have to go to have one day where the sun would not set. And on December 22nd at the Arctic Circle, 66.5 degrees north, the sun would never rise. You'd have to, again, go that far north to have a day where the sun would never rise. And I've been up there for that, or close to that, and it's pretty freaky, pretty weird. How much of the sun's shortwave radiation is reflected, scattered, absorbed before making it to the surface? The sun is a very hot object, so on average it gives out shortwave radiation. That's energy coming from the sun. So not all of it makes it to the surface of the earth and is absorbed. Maybe about half does. Okay, that energy that reaches the surface of the earth and is absorbed is called insolation. So on the way in, only half makes it to the earth and is absorbed. So we're going to say 25% gets reflected. That's off of like snow and ice or clouds, things that are light in color. 5% is scattered. That's when a shortwave energy from the sun hits like an N2 molecule or an O2 molecule or a small particle in the atmosphere, and the rays go off in different directions. The reason the sky is blue is because it just so happens that the blue part of the visible spectrum, visible light is composed of many different colors. All right, you see this like in a rainbow or something. So nitrogen and oxygen are really small, so they scatter the shortest wavelengths, which are the violet and the blue. Okay, about 20% of the energy is directly absorbed, and a good gas for that is ozone up in the stratosphere. So the answer to this is about 25% is reflected, 5% scattered, and 20% directly absorbed in the atmosphere. Know the freezing and the boiling points on the Fahrenheit and Celsius scales and how to do conversions between the two scales. So I'd like you to look up the formulas. You can just write those down, how you change Fahrenheit to Celsius and Celsius to Fahrenheit. You guys can do that. As far as the freezing and the boiling points, on the Fahrenheit scale, at sea level, the boiling point for H2O is 212, and the melting point for an ice cube, or the freezing point for you guys, is 32. The Celsius scale would be 100 for the boiling point and 0 for the freezing point. Understand how to figure the average annual temperature range and where in the world one might experience the largest and smallest ranges. So by the way, when you're doing these questions, I want you to type out the questions and the answers, okay? So I know it's a lot of work, but please do that for me. The largest average annual temperature ranges will be in the middle of the large land masses, like in the middle of Siberia. So the average annual temperature range is the difference between the warmest monthly average and the coolest monthly average. So land surfaces heat and cool more rapidly than water. So if you go to the middle of Siberia, you might find like a 120-degree difference between the coolest monthly average and the warmest monthly average. Now to find the smallest one, you want to go over water at the equator. At the equator, day and night are always equal, and water changes temperature very, very slowly. Right? Very slowly, large bodies of water. So maybe if you're over land, find a dot, smallest island you can, on the equator. It might, every month might average like around 80 degrees, just beautiful weather. Understand the relationship between maximum temperature and maximum insolation. Okay, so on a daily basis, maximum temperature lags behind maximum insolation. Insolation is energy that makes it to the surface of the earth and is absorbed, and you know what temperature is. So on an average day like in Visalia, the most direct rays are coming in at noon, but you know that it gets the warmest, generally, especially in the summer, about 5 or 6 o'clock in the afternoon. So on a daily basis in the mid-latitudes where we live, maximum temperature lags behind maximum insolation 4 to 5 to 6 hours. On an annual basis, the temperature lags about 4 to 6 weeks. And maximum insolation in Visalia comes on June 22nd, the longest day of the year. But you know, the warmest days generally come at the end of July and early August. What are isotherms, and how do you recognize a weak or a steep temperature gradient? Isotherms are lines, like on a weather map, that connect points of equal average temperature. A steep one means the lines are close together. That means as you travel across them, the temperature changes very rapidly. A weak one is if the isotherms are more spread out. So as you travel across them, the temperature doesn't change very rapidly. Land-water contrast, I mentioned this a little bit just a moment ago. Large bodies of water moderate the temperature because they heat and cool very slowly compared to land. Like the ocean out here in front of me, it takes a lot of energy to heat that up and cool it off, right? A lot of energy to heat it up. It takes a lot of time to cool it off. Because the water is transparent, the energy goes in and can get mixed around at deeper depths. On land, the energy might be focused on the top inch or two, and that's it. So that land surface can heat up quickly and cool off quickly. So I'm in Morro Bay right now because I live right next to the ocean. I feel very lucky. Summers don't get as hot as Visalia and winters don't get as cold because it's a large body of water. And it takes a long time to heat it up and a long time for that ocean to cool back off. And I'm going to turn it over, second page for you guys. What causes seasons? Basically, it's the tilt of the Earth's axis. Right? The North Pole remains pointing the same direction in the sky all the time as the Earth revolves around the sun. You saw that in one of the handouts, one of the exercises you had to do. I think I showed that to you. So as a result of that, the sun's rays will strike at different angles, different times of the year at various latitudes. And that affects solar intensity, the amount of energy striking the Earth. Therefore, that affects seasonality. The short answer is, what causes seasonality? The tilt of the Earth's axis. Wien's law. Wien's law is something that I learned in my physics class from good old Dr. Wien, right? That every physical object in the universe radiates waves, right? Okay? And Dr. Wien would say the hotter the object, the shorter the collective batch of waves it emits. The cooler the object, the longer the waves. So as far as meteorology goes, the sun is a really hot object compared to the Earth. Average surface temperature, maybe 10, 11,000 degrees. The Earth is approaching 59 degrees Fahrenheit. So the sun gives off shortwave radiation compared to the Earth. The Earth will take in shortwave radiation from the sun and re-radiate it in the form of longer wave radiation, which happens to be trapped effectively by CO2 and H2O. That's carbon dioxide and water vapor. And that trapping of the long wave energy from the Earth, of course the ultimate source would be the sun, but the Earth re-radiates it. The trapping of that energy by CO2 and H2O keeps us warm here near the surface. That's called the atmospheric effect. If that were not going on, it'd be, as I sit right here, it might be 60 degrees colder. So that's a natural thing, and we really like that. So as far as Wien's law goes, Wien's law would say that every physical object in the universe radiates waves. And the hotter the object, the shorter the waves. The cooler the object, the longer the waves. What surfaces have high or low albedos? Albedo measures the reflectivity of various surfaces. So something like clouds and snow and ice would have a high albedo. In other words, a lot of the energy that comes in gets reflected back, whereas something like asphalt, right, would have a very, very low albedo. It absorbs a lot of heat. It's a hot summer day, and you're at the 7-Eleven on Mooney Boulevard. You're walking across Mooney Boulevard barefoot. You're probably walking on the white crosswalk lines because they're reflecting a lot of energy, and they'll be cooler, whereas the asphalt is absorbing a lot of that heat. On a daily basis, where are you likely to experience the highest and the lowest temperatures? Or when are you? Generally 6 a.m. for the lowest temperatures because the Earth has been giving off that energy all night, that long wave radiation. And the highest temperatures are usually in the afternoon, right? In Visalia, good summer day, 5 o'clock, correct? What atmospheric gases are primarily responsible for creating the atmospheric effect? Again, we talked about that just a moment ago with Wien's law. That would be CO2, carbon dioxide, and H2O, water vapor. A radio sound is it's a balloon that has weather instruments attached to it that are sent up from various locations around our state and around our country each day. And they go to the higher atmosphere and they take weather readings in the upper atmosphere. The difference between the homosphere and the heterosphere. Okay, in the atmosphere, there's 4 basic layers. There's the troposphere, where I am. Next layer up is the stratosphere, then the mesosphere, then the thermosphere. The bottom 3 layers collectively are called the homosphere. So that'd be the troposphere, stratosphere, mesosphere. It's called the homosphere because the gaseous composition is roughly the same. It's going to be 78% nitrogen, 21% oxygen, and lots of other trace gases. The highest layer is called the thermosphere. It's also called the heterosphere because The gases are layered up there based upon weight. There's not a lot of mixing going on. What does cloud cover do to daily temperature ranges? Cloud cover reduces the daily temperature range. Okay? When you have clouds during the day, like some are moving in right now or the fog's rolling in, that's going to reflect incoming shortwave radiation. Whereas any energy that makes it through the fog or the clouds and gets to the earth and is absorbed and re-radiated is trapped by this fog and trapped by clouds, correct? And so that's the atmospheric effect. So what clouds do is they reduce the daily temperature range. Okay? The temperature doesn't change that much during the day when it's cloudy. Okay? Hypoxia. I think that's a kissing disease that went around in about the year 2017 at Golden West High School. Just saying. Hypoxia is also altitude sickness. Forget the two matching sections. For your essay, you're going to answer all three parts. You're going to type everything for me. I'm going to turn this in as one file, one Word doc, hopefully. And I would think, I put in instructions, I don't have it in front of me, but generally 12-point font, I don't think you need more than a page and a half, how many words that comes out to be. Certainly no more than 2 pages on this. Give me 2 citations other than me in your book, all right? Give credit where credit's due if you use somebody else's words. So basically, here we go. Global warming, my definition is that it's an unnatural warming of the atmosphere, primarily as a result of the burning of fossil fuels and slash and burn deforestation. So fossil fuels would be oil, coal, natural gas. Slash and burn deforestation takes place in places like the Amazon Basin in South America, in the Congo Basin, right? The Zaire Basin in Africa, Equatorial Africa, the western part of Africa, Indonesia, right? Places where it's tropical. So people will cut down the forest, then they'll burn it, and that ash, the ash acts as a short-term fertilizer, and they'll farm, but soils aren't that good. They move on usually and slash and burn some more. So when you slash and burn the forest, okay, CO2 is released into the atmosphere, correct? And when you cut trees down, it's like a double whammy because the tree's no longer there to take in CO2, plus when you burn it, you release CO2. When you burn fossil fuels, that releases CO2 in the atmosphere as well as other gases. So the principal greenhouse gas is CO2. We know CO2 traps heat. It's not the only greenhouse gas. There are many others, like some of the oxides of nitrogen, NO, NO2, CH4 is methane. Ozone near the surface as an air pollutant traps heat. So there are many other greenhouse gases. So if the concentration of these gases goes up, and apparently it has been, and we know these gases trap heat, the theory says temperatures should rise accordingly. And apparently they have been. Based on what study you look at, I'll give you some average numbers. Since the U.S. Industrial Revolution started around 1880, temperatures have gone up maybe a degree and a half. And it appears that they're continuing to warm up at the present time. Part 2, explain the general theory of stratospheric ozone depletion. Ozone is primarily located in the stratosphere. That's where we want it. We don't want it here near the surface because it harms our lungs. So in our respiratory system, other parts of our respiratory system. So it's still a trace gas. You know, probably 90% of ozone is in the stratosphere, the next layer up, but it makes up a minute portion of the stratosphere's total volume. Why is it important? Because it absorbs shortwave radiation, absorbs ultraviolet light. And long-term exposure to ultraviolet light can damage your skin, for fair-skinned people like me. I'm struggling with this, no skin cancer yet, but I think I'm getting close here living at the beach. But it can damage your eyes, it can give you cataracts in your eyes, it can possibly damage your immune system, it can damage some of the plankton in the ocean, I've read, and that's the base of the marine food chain. Okay, so beginning back in about 1927, Evil Giant fans, now they're San Francisco Giants, they were probably New York Giants at the time, started using these chemicals, these things called chlorofluorocarbon, CFCs. And that's chlorine, fluorine, and carbon, and the culprit is chlorine. The chlorine can disrupt the ozone layer. Fortunately, the big dodger in the sky has it set up so ozone is forming naturally all the time, as I speak. But these compounds, like CFCs, have been disrupting the ozone layer. What have we used CFCs for? Well, we've used them for air conditioning. Freon is a type of CFC, the production of foam products, insulation. So CFC is another group of compounds that has disrupted the ozone layer called halons. Chlorine is not the culprit, as bromine or bromine is the culprit with the halons. And the primary use that I know of for halons has been fire suppression. And fire extinguishers are putting out big oil field fires. There are other compounds that have disrupted the ozone layer. Methyl bromide is one that is still used a lot in the Central Valley in agriculture. Some good news, there's something called the Montreal Protocol that was passed back in the 1990s, and most nations of the world have signed on to the Montreal Protocol, and it is limiting ozone depleting substances. So we no longer make chlorofluorocarbons in this country. We've come up with safer substitutes. They're called HCFCs and HFCs. They have disrupted they're safer substitutes. The lifespan in the atmosphere is not as long. So for this part, stratospheric ozone, you want to say that it's ozone is primarily concentrated in the stratosphere. It's a trace gas. It's important because it absorbs ultraviolet light. Long-term exposure to ultraviolet light can damage your skin and your eyes. You maybe want to mention chlorofluorocarbons and halons in your discussion. Part 3, are there any interrelationships between these two problems? Well, they're both human caused, evidently, and they can both lead to heating up of the planet. If you allow more shortwave ultraviolet radiation to hit the Earth, that's going to help warm up the Earth. And then at the same time, if you have a higher concentration of CO2 and other greenhouse gases, it's going to trap that long-wave radiation coming back from the Earth. So ozone depletion lets more shortwave in. The global warming will trap more of the outgoing radiation. So again, a page or two on this, max. I'm fine. If you want to write more, you can, but honestly, there's not enough you in the world, right, to read too much of this stuff. So anyways, good luck on this, and I'll check with you soon.